So, welcome to the second session of today, which is going to be dealing with the energy production. Today we have four wonderful speakers that are going to be talking to us about geothermal energy and shale gas. And I think what's different about this session is that they're going to be talking about the environmental impacts of the industries that they work in. So it's going to be really good, and I really encourage the students to ask some questions during the panel. So our first talk is going to be geothermal energy production in Cornwall and its expected environmental impact. We have two speakers for this session. The first is Lucy Cotton. Lucy is the project geologist for the United Downs Geothermal Project in Cornwall. She's a trained exploration geologist, and she focuses on characterizing regions for potential geothermal developments. She's been involved very closely with the technical development of the United Downs Geothermal Project and also with their educational outreach program. And that has played a very, very key role in project acceptance in the community for this geothermal project. Our second speaker is Andrea Paulillo, and he's a postdoctoral research associate at UCL. He's part of the Science for Clean Energy project, and he specializes in developing the life cycle assessment method, focused particularly on energy systems. And in Science for Clean Energy, he works with geothermal energy and CO2 storage. So welcome.
Okay, thank you, Catalina. Okay, so Andrea and I are going to talk about the geothermal energy in the UK and its expected environmental impacts using United Downs as a case study. We know that deep geothermal energy is a renewable energy resource, but how environmentally beneficial is it really? And how does it compare to other energy resources? Particularly, how does it compare to renewable resources? These are all things that Andrea will address later in the presentation, and I will give you an overview of Cornwall, why we chose Cornwall to develop the UK's first geothermal project, a little bit about its geology, the project concept, and where we've got to so far. So, why Cornwall? Cornwall has the highest geothermal gradient in the UK, and that's because of its granite. The county is underlain with granite throughout, and it outcrops in various places in the county. We're targeting a granite outcrop called the Carmenellis granite, and this granite elevates our geothermal gradient to 33, 35 degrees per kilometre, compared to the rest of the UK, where it's about 26 degrees a kilometre. And even though it's small, drilling's very expensive, so any gain you can have is worth having. As well as a heat source, Cornwall has a family of faults that run across the county, which promotes permeability at depth. And these faults run from the northwest to the southeast of the county, and you can see them outcropping at either coast. Our fault zone that we're targeting in the project is called the Porthtowan Fault Zone. And these north-northwest, south-southeast faults have a multi-phase history and are associated with fluid flow from the Permian right to the present day. And I'll go through a few examples of fluid flow evidence within these fault structures later. Our location, this is the most west point of the peninsula in Cornwall, and we're sort of in the middle of that. And the reason we chose this location is because it's close to the Porthtowan Fault Zone, and we can intersect it easily with directional drilling, and it's also on a brownfield site. So if we're talking about climate change and sustainability, it's important to be as sustainable as possible with these sort of sites, and brownfield over greenfield is an easy start. In terms of why we're targeting the Porthtowan Fault Zone, this area has a huge mining heritage, and there's a lot of data in this area from the mine works. And within those mine works and the data, there was found thermal springs along the cross-core sections, which is one of our target faults. And these thermal springs measured temperatures of 60 degrees at 400 meters, which is way above the geothermal gradient and provides evidence of deep fluid flow. As well as that, you get occurrences of uranium, which is a mobile element. And also, along these structures through the county, there's evidence of hydrocarbon seeps. And the nearest hydrocarbon rock to us, or it's been dated to be from the Bristol Channel, from those Jurassic source rocks. So that's a long way from us, and it's evidence of long, far-field fluid flow, which makes these potentially good targets for geothermal reservoirs. The project concept was to drill 2 deep wells, and again, Andrea will cover the environmental performance of the project in regard to how much carbon does the drilling actually take. We drilled 2 wells, one to 5,275 meters, that's the production well, and the other one to 2,394 meters. Both wells intersected the target structure at depth, which is great. And the idea is we'll bring hot water from depth up to surface via the production well, put it through a heat exchanger to generate electricity, and then re-inject that water down the injection well. This will be a closed-loop system, so as it's sustainable, and it will be a binary plant at the surface that does the electricity. So far, we started drilling a year ago, nearly to the day, on the 7th of November 2018, and we completed the production well in April. The production well has 4,000 meters of casing, and again, Andrea has looked at the environmental performance of that and the carbon used to produce the steel to go into the well. These are all things that have been looked at in a life cycle assessment. We then drilled the injection well and completed that in June, and are now in a phase of building a lagoon on site so that we can do a production test and put the produced fluid into the lagoon. At the end of January, in February, we'll have a workover rig come to the site, and we'll do a static temperature log so that we can get a true temperature reading. We haven't got one yet, but we do know that it's hot down there. And we'll then get some sidewall cores from the fractures to see what the fracture fill is. So if we need to do any stimulation, some tests can be done on those cores, on those sidewall cores. And we'll do an airlift production test as well, see what our production rates can be. So far, we know that the temperature is good. We haven't been able to get a core reading, but whilst we were, just after drilling, we took a temperature log and it was 180. So we've predicted that it's going to be 193, 194 degrees, which is bang on what we predicted. We know that there are fractures present at depth because our image log results are very promising. There's a lot of fractures within our target zone. And we know that injection is possible, which is a big one. We did a short injection test at the end of drilling the injection well, and we managed to inject at 60 litres a second, which is our target flow rate for production. So that's good news. What we don't know is the circulation rates between the 2 wells and what our production rates will be. So that's crunch time. That's what we've got to find out in February. It's worth saying as well that our injection, our base case is to produce 1 megawatt of electricity, and if it goes well, then we can extend that to 3 megawatts. And Andrea will look at the difference and the environmental performance of the wells between 1 megawatt and 3 megawatts. So I'll pass you on.
All right. Okay, after we have learned a little bit about the United Downs project, let's look at the expected environmental impacts. So to quantify the environmental impacts, we used a methodology called life cycle assessment. This is a standardized methodology widely used in the UK, in Europe, and indeed in the world by both the academia and the industrial world, industrial sector. So basically, life cycle assessment has 2 main features or advantages. First, it looks at all the phases in the life cycle of a product or a service, so starting from the extraction of raw materials up to the management of the waste in the end of life. And second, life cycle assessment covers a broad range of environmental issues, which include but are not limited to climate change impacts. So how do we perform LCA? In short, to make it very simple, the first part is to compile, to gather data, what we call input-output data on the process under investigation. So we look at, for instance, the energy consumption, the materials and chemicals used, the emissions to air and discharges to water and soil, and the amounts of products, co-products, and wastes that are generated throughout the life cycle. In the second step, we use environmental models to translate this data into potential environmental impacts on the environment and on human beings. For instance, as I said, we look at climate change, but we also look at other potential environmental issues, such as formation of particulate matter, cancer and non-cancer effects due to toxic pollutants, acidification of fresh and seawater, and so forth. So for the United Downs project, we divided the life cycle of the project into three main phases, of course: a construction phase, an operational phase, and an end-of-life phase. In the construction phase, we looked at the construction of exploratory wells, the construction of the injection and the production well, the construction of collection pipelines, and the power plant, which will produce the electricity. We also looked at a number of other activities that may be required in case the productivity of the well is not sufficient. And these include, for instance, chemical and hydraulic simulation, which essentially consists in pumping acidic chemical or pressurized water in the well to increase the productivity, increase the extent of the fractures. We also looked at the construction of a second leg in the main production well, again to have the same result, which is increasing the productivity of the well. Now, the operational phase only includes the generation of electricity, but we also looked at the possibility of co-producing electricity and thermal energy, so hot water. And finally, the end-of-life phase consists in the closure of the wells and in the decommissioning of the power plant. Okay, so let's look at the results of our study. We'll mainly focus on the climate change impacts, but what is important is that the discussion about these results can be applied to other environmental issues. So the main conclusions can be applied to other types of environmental impacts. So in this bar chart here reports the contribution analysis for our base case. Contribution analysis so reports the contribution of each element to the overall impact in the climate change category. So our base case scenario is, as Lucy said, a 1 megawatt installed capacity. There is no need for stimulation or enhancement technique, so the productivity of the well is sufficient. There is no cogeneration of hot water, and there is only one pump in the production well. What we can see from here is that over 90% of the climate change impact are due to the construction of the production and the injection well. And indeed, what we found was very interesting is that most of these impacts originates from two key elements. These are the amount of diesel that is used for drilling, so for powering the drilling rig, and the amount of steel used as casing in the geothermal well. Then, as I said, we looked at a number of scenarios, and how this could affect the overall environmental performance of the project. So, for instance, in case the productivity of the well is not sufficient, and in case we need to carry out stimulation or enhancement techniques, this can, of course, increase the impact in the climate change category, and in the worst-case scenario where all these three activities are required, the impact could increase by around 30%. Now, indeed, the most interesting results are those that relate to possible other configurations of the plant. So in case the installed capacity is increased from 1 to 3 megawatt, then this would yield a reduction of about 66% in the overall climate change impact, because basically the production of electricity is much more efficient. And also, in case we could generate thermal energy and electricity, then we would have a reduction of about 60%. So basically, the project, the production of electricity would be much more efficient in environmental terms. Okay, but then we ask, okay, how does geothermal energy compares with other energy sources in the UK? So what we did, we compared UDDGP, which stands for United Downs Deep Geothermal Power Project, with electricity produced from natural gas, from nuclear, so a typical pressurized water reactor, photovoltaic solar, and offshore wind. What we found is that the geothermal energy in the UK has the third lowest carbon footprint after nuclear, the green one, and wind offshore. So it has a very good performance, right? But what about other environmental impact categories? So we compared the same for other environmental impact categories. And here the results are more mixed. So in some categories, geothermal energy performs very well. In other, it performs a little bit worse. So for instance, in the photochemical zone creation category, as an example, geothermal energy is actually the worst performing technology. So here, the key message is that there are always trade-offs to be considered. There isn't one technology which is the best technologies in all environmental impact categories. So every time we make a decision, every time the decision maker takes a decision, right, they have to consider these trade-offs and then weigh them, and on this basis make the decision. And that's why life cycle assessment is such a fundamental and powerful tool. So in conclusion, we have seen that the construction phase is the most impactful phase in the life cycle of producing electricity from geothermal energy in the UK, and in particular, the impacts originate from the use of steel and diesel. Then we've seen that the most effective strategies to reduce environmental impact are either increasing the installed capacity or co-producing hot water and electricity. And finally, we have seen that there are clear trade-offs when we compare different energy technologies, but that for climate change, geothermal energy in the UK is actually the third best performing technology after wind and nuclear. Thank you.
Hello? Yeah. Any questions for Andrea or Lucy?
Lucy.
I have a question for you, Andrea.
Okay.
So you mentioned that geothermal energy is the least performing technique for photochemical ozone formation. So
yeah.
could you please explain a little bit?
Yeah, so basically this category, first of all, is strictly related to the diesel. So when you burn diesel, right? So that's why it's so high. And actually, one thing I should say is that United Downs, the project, is actually planning for future wells not to use diesel, rather electricity. So there would be a bigger increase in environmental performance of geothermal energy. Now, this category basically relates to the formation of what's called summer smog or Los Angeles smog. It's basically when you form ozone in very low in the atmosphere. So ozone in the higher part of the atmosphere is good, as we know. In the lower part, it's not good because it can cause damages to plants or damages to detrimental effect to humans. And basically, it's formed when you have nitrogen oxides and volatile organic compounds. Basically, they react and they form ozone. But basically, what's important is that this is related to diesel, when you burn diesel.
Thank you.
Any other questions?
Thanks. One question for Lucy first, and then for Andrea. So Lucy, you both referred to using heat as well as power. Can you tell us something about maybe some of the discussions you've had about with the local community and potential heat users and also the community about using that heat?
Yeah, the heat, we haven't decided what we're doing with it yet, but we have talked to the communities, and they're clearly interested in district heating schemes, but the local village is quite old and it's really hard to retrofit a heating scheme. So we've talked about greenhouses, there's been talk about swimming pools and that sort of thing, but we've been very open with the community and we're very open to having their involvement with it. It's something that we can work on once we know what we've got down there, basically. It will come later. But moving forward, if we're looking at other projects and that sort of thing, we'll put that at the forefront of the planning as well, so it's integrated within the project.
Thank you. And a question for Andrea then. So obviously with a well of this depth, you have to be talking about steel casing, production tubing. If you're talking about differentiating this project that is about power with geothermal heat projects, a lot of particularly closed cycle ones are using polythene pipe rather than steel casing when they're multiple wells at a couple of 100 meters, say. Have you looked at that at all as a methodology, or do you see any potential for using that to establish the credentials of that with your methodology?
Okay. No, I haven't looked into that, but basically because as I understand, when you have such deep wells, you need steel to support the structure of the well. But one recommendation could be simply to increase the recycled content of steel, if you can do that. Because in that way, you are not actually using raw steel, you're using pre-used steel, so in a circular economy perspective, and that would be increasingly, I think it would be very good for the environmental performance of the project. And as I said, the other main recommendation is about replacing diesel with electricity. This also would decrease the environmental impacts by a substantial amount. But definitely I need to look at when we are talking about shallower wells, the use of alternatives to steel.
Okay, thank you. Maybe we can do the rest of the questions during the panel.
All right.
Thank you. Okay, our next speaker is Jörg Ude, CEO of Alsvarke GeoFuture Limited, which is the owner and operator of the Insheim geothermal power plant in southwest Germany. So thank you for coming today. He has a wide expertise in mining, drilling, and geothermal projects. And in his current position, he's joining forces with other researchers to develop the lithium extraction techniques from the geothermal brines. So welcome and thank you for joining us today.
Thank you very much for your kind introduction. Well, we have heard now a lot of talks about science and what we could do out of our geothermal potentials, but now I will give you a talk about how it's really going on and what are the demands when operating a geothermal power plant. Well, I will concentrate a little bit on the project history, the technical data, how did we develop our reservoir. Seismicity impact mitigation is a very interesting topic in regards of public acceptance. And then we have a lot of operational challenges I will focus on, and by the end, of course, I come back to the lithium topic. I think there went something wrong. Okay. So this is the geothermal power plant in Insheim. It's now 7 years in operation. The main elements of the power plant are the production and the re-injection well, pretty close by. We will later see how the wells have been drilled, the grid connection, the control room, a very large unit is the air-cooled condenser, the thermal water treatment, and the power generating facility. It's an organic Rankine unit. So how did we develop our reservoir? 9 years ago or even 10 years ago, the data available were very small. We just had 3 2D seismic lines, and so it was a very demanding task to develop and to the reservoir model and to define the fault structures which have to be developed later on. And this is one picture of the reservoir model which was later designed. We addressed 2 fault systems. One we drilled in with a production well, and later on the injection well. It was definitely the first well which has been drilled. And after executing the production test, it was later decided to have a multilateral completion for that well. So a sidetrack has been drilled to enhance the permeability on the re-injection side, which was definitely a very good decision. Actually, we get the thermal water out of 3 geological sections, from the limestone, the sandstone, the Bund sandstone, and from the fractured granite in the bottom hole section, which is unfortunately on the production side less permeable than initially expected. The technical data: the power plant was designed for a flow rate of 80 liters per second and the brine temperature of 165 degrees C, which definitely will be reached in the operating facility, but unfortunately we haven't reached so far the design point of 80 liters per second. We're operating the power plant at the moment at 70 liters per second. Therefore, in cold winter times, we generate around 4 megawatt up to 4.2 megawatt of electricity. The availability, fortunately, is a lot better than initially expected. The power plant is operating around 8,300 hours up to 8,350 hours per year due to a very intense maintenance scheme. Actually, we do not have a thermal energy output at the moment, but we are in very promising discussion with an investor for planning a greenhouse facility with a surface of 15 hectares, just 1.5 up to 2 kilometers close by. This would offer an option to deliver 6 megawatt thermal constantly over the year. We expect the final decision this year before Christmas. The on-site power demand is about 25%, so this, of course, is an issue when having the climate impact of a power plant, as in when rising ambient temperatures in the summer, when we have ambient temperatures of around 30 degrees up to 35 degrees Celsius, the electric power is reduced up to 1 megawatt electricity due to the reduced performance of our air condenser. Therefore, I will come later back on this. We are discussing methods to optimize the system. The financial basis in Germany for geothermal power plants is the German Renewable Energy Act. We receive a remuneration for 20 years for 25 euro cents per kilowatt hours. So we have 13 years in advance. And this covers basically the CAPEX and OPEX of a power plant. There is no geothermal power plant in Germany which has so far reached the initially promised high revenues of 10 or 12% over the year. So the most of the geothermal power plants just are writing, as we say in Germany, a deep black zero on the profit loss scheme. The total expenses of the investment have been around 50 million euros, which will be necessary today. I guess you will need at least 10 million more due to rising prices. This is the basic theme of the binary power plant. This is the thermal water units. We have the production well. We are pumping the thermal water at a depth of 700 meters depth to the surface, transfer the heat of the brine through a group of heat exchangers to a binary system, which is working with 40 tons of isopentane. It's an Ormet organic Rankine circus, running very, very reliable, so we are very happy with this technology. And the isopentane is, after it has been decompressed in the turbine, condensed in the already shown air cooler, and then reheated and vaporized again, and the cooled brine is re-injected in the re-injection well. While operating our thermal water circuit, we have always to face natural seismicity as the Rheingraben, the area we are operating. Our system is still a very active geological area, and therefore we were obliged to have a very tight control system. So our power plant is one of the densely controlled geothermal power plants in the world. We have a very tight network of seismic sensors and of ground velocity sensors, which are permanently online. So, for example, at the moment, earlier this morning, I received a short message that last night we had a seismic event of 0.7. So this is not critical, but we have to be aware. And as I earlier said, operating the thermal water circuit is always riding on the razor's rim to be. And due to past discussion with very critical public initiatives, a seismic impact mitigation traffic light system has been developed. And just concentrate on level 4. This is the reference value of a technical norm we have to respect in Germany. This is the 4150 norm. So new buildings have to withstand 5 millimeters per second, and existing buildings should withstand 3 millimeters per second. But when you're looking on the left side, we already have to react at the 10th percent of this value, and even these values occur probably once or twice a year. So we are very carefully operating our system so that we never reach these areas. And this complies quite tight to the traffic light system, which is published in Great Britain. So it's almost the same scheme behind. And when operating a thermal water circuit, we have to respect this. Otherwise, we will have the public on the fence of our power plants. As well, of course, we have to address the public, especially in our area. We have a lot of critics in the public, which is quite different from the other major geothermal area in Germany, the Bavarian Balassi Basin around Munich. They have a very excellent public acceptance for what they are doing there. This is quite different in our area in southwestern Germany. So we have to invite the public to show what we are doing, as we believe we do the right things right. And you cannot stop repeating this constantly. And as well, we have to convince the authorities that, for example, we have to prove the well integrity after 7 years of operation. This was a very expensive logging operation with Halliburton earlier this year in September. We did this just to prove that the well is in a perfect shape and that we have an excellent database. As well, due to the fact that we are operating the power plant with 40 tons of explosive isopentane, we have to comply to the public law, and every 3 years we have a civil protection exercise. Every year we have additional exercise with the local fire brigades so that we can be sure that they're very compliant with our side, that they know what to do when something might happen. As well, as you have seen in the aerial view earlier, we have a vineyard close by, and so once a year we buy a portion of the wine production from this vineyard, and we will deliver it to visitors. So whenever you come by to visit our power plant, and you are heartily invited, so then there will be a bottle of this excellent dry Riesling for you. Well, the operational challenges, of course, I already mentioned our thermal water pump. We are pumping the water with a line shaft pump, which is installed at 740 meters depth, so it's one of the deepest installed line shaft pumps in the world. It's a very reliable system. We have a 39-stage centrifugal pump installed at 740 meters depth, so 200 meters below the groundwater level. And this pump has to be serviced every 5 years, for example. This is a very expensive operation, costing, including the loss of operation revenues, 1.5 million euros, the workover of this pump, so it shouldn't be done that often. And when restarting our power plant to heat up the brine and the production and the reinjection well, then we have these steam emissions, and this is always a reason for discussions with the public. But hopefully this happens only twice a year. Then as well, due to the fact that we get a portion of our brine from the fractured reservoir, from the granite, so we have to deal with these Tnorm issues, which is very complicated in Germany, as we still have a lack of regulations to get them disposed of. As well, we have a corrosion issue with our brines. Therefore, we had very intensive R&D works in the past years, and we succeeded to reduce the amount of scales dramatically from initially about 2 to 3 cubic meters per year, and the cost of disposing of these scales are about 10,000 euros per ton, including development and especially receptors, as they have to immobilize to get them disposed of. So we have to double or even more enhance the quantity of these scales. And during our last maintenance operation this year in September, we were very happy that we could reduce the amount of scales from initially 2 to 3 cubic meters just to 20 liters per year. So this is a dramatic step forward. And as well, a change of materials. So to use this material helps to reduce corrosion effects in the brine circuit, but it's possibly only to use it on the returning circuit on the low temperature side below 100 degrees C. So coming to an end, lithium in the geothermal brine, we have an interesting content of 180 to 200 milligrams per liter lithium in the Rheingraben, in the brines, not only on the enzyme side, but as well on all the other sides, on the French side and even on the German side. And even if you consider that we might get 50% of the lithium contained out of the brine, it is a very promising business, but there's still not appropriate technology available. And as well in Cornwall, a company, Cornish Lithium, is working on that topic as well. In France, our colleagues are working on the topic as well. It's probably something like a gold rush. Everybody wants to have it, and we are actually close to an Australian investor to install a first pilot plant on an extended laboratory scale to evaluate the influences on the brine circuit. What will happen if we cool down the brine further down? We will get further scales then, especially silica scales. We have to prevent the brine from that. And so this will be a very interesting issue. When we will be successful, the potential turnovers will exceed the turnovers we will have with the power production. Yeah, this is a short overview of the well-known Energiewende in Germany. This is a nuclear power plant to be shut down by the end of this year, so shortly before Christmas. This is the first generation of windmills close by to our geothermal power plant. And the annual power production of these windmills is roughly the same of ours, but we have a constant power production of 8,300 hours per year, and these windmills work roughly about 1,200 hours per year. So this is typically base load and a very small footprint, as you can see. Yeah, thank you for your attention. I hope I kept the 15 minutes limit, and keep in mind, geothermal is the energy under our feet and will be the future for us. Thank you.
Thank you very much. We have time for questions.
How long does it take to take the production pump out of the well, service it, and put it back?
Well, when everything is well prepared, the workover period with extraction and then reinstall, 2 weeks, I would say.
Thank you.
Any other questions? Yes.
You mentioned that your site was a kind of an outlier in terms of public acceptance. I'm intrigued. Why is that so? What's so special at your site?
Well, it's not that special. Well, sometimes missing public acceptance was caused by a previous geothermal power plant, the Landau power plant, which is pretty close by, which is a previous generation, which went in operation now 10 years from now. And Landau had a problem with the permeability of the reinjection well, and to enhance the permeability of this injection well, a stimulation process was done. So water was pumped with high pressure into the reservoir to enhance the permeability of the reservoir, and this caused a seismic event 2 weeks later of about 3 to 3.5 on the Richter scale, in combination with a supersonic sound wind when the air was blown out of the well. And this was the initial event to cause public initiatives against the geothermal. And basically this was another reason to have this multilateral completion with our reinjection well that my predecessors have drilled a sidetrack there.
Thank you. Okay.
I mean, you've obviously, the industry, we've all learned a lot from Landau coming forward to the plant you're now operating. I mean, if you imagine another reservoir development and plant in 10 years' time or something, in what ways do you see it being different to what you are working with just now in terms of, the whole development of the reservoir and the plant and the whole thing?
Well, it's quite easy to answer. I think the future will be multilateral completion of a reservoir. So if we have this major pre-investment in developing the reservoir by drilling these deep wells, our wells have a final depth, a measured depth of more than 4 kilometers and a vertical depth of 3.8 kilometers. So 50% of the overall investment is buried in the wells. And when you consider this 50% of this pre-investment is combined with a very high risk, as we do not know when drilling the first well, will it be successful or not. And even we still have a serious risk when drilling the second well, as only when we have drilled at least the first doublet and have completed our production test, then we can be happy or not. And we learn a lot while drilling. So I think in Cornwall we have learned this as well. I think drilling the second well was a lot easier, but drilling the first well, if you have a deep information about the reservoir and the geological environment, and therefore it's reasonable to drill more than 2 wells, at least 3, probably 4, to enhance the reliability of the power plant, to enhance the power output, as 4 megawatt is not that much in terms of the investment amount. And the major advantage is if you operate a double-doublet system, at least you can operate your system while servicing one of your production pumps. You have at least 50% of the production available, and you do not have to shut down the whole power plant, which costs a lot of money.
Okay, thank you very much for your presentation. Now for our last speaker, we have Professor Fabio Ribeiro from Purdue University. So thank you for coming so long. He's the director of the National Science Foundation Engineering Research Center called Seastar, which aims to convert light hydrocarbons from shale resources into chemicals and transportation fuels. So I am really looking forward to your talk. Please, welcome.
Thank you, Catalina. Seastar, the Center for Innovative and Strategic Transformation of Alkane Resources, is the right team with the right idea at the right time to address major U.S. energy and manufacturing opportunities. 90% of transportation fuel and more than 80% of U.S. chemicals, including plastics, come from oil. The U.S. uses about 10 million barrels of this oil each day to transport people and goods. That many barrels, stacked end to end, would stretch across the country twice every day. We all agree our best long-term energy solution will be to replace fossil-based fuel with renewable sources. It will take many, many decades to economically develop renewable sources to replace fossil fuels. Until that time, we will continue to use oil. Rather than importing the oil we need, a tremendous resource exists right here in the United States. We have more than a 100-year supply of energy in shale that we can use as bridge fuel until renewables can support our needs. Shale resources include a complex mixture of light hydrocarbons trapped in shale formations. However, this gas is not in a form that we can easily use. Our goal is to develop new technologies needed to economically convert shale gas into transportation fuels and petrochemicals, which will also reduce carbon emissions. In fact, U.S. energy-related CO2 emissions are already decreasing as natural gas replaces coal. Seastar will accelerate this decrease by improving the value of natural gas and by creating a fuel that emits less CO2. Seastar is one of the newest flagship engineering research centers funded by the National Science Foundation. Innovative technology will enable us to responsibly convert light hydrocarbons from shale, reduce carbon emissions, and reinvent the transportation and petrochemical industry through small, mobile manufacturing plants strategically located close to America's vast shale reserves. Seastar will bring new jobs to many rural communities and ultimately inject an estimated $20 billion annually into our nation's economy. We will also prepare the next generation workforce to deliver this energy revolution. Our interdisciplinary and inclusive team has diverse learners, researchers, and educators from engineering, science, and policy. The Seastar innovation ecosystem brings together stakeholders who are able to translate scientific breakthroughs into commercial solutions. Seastar has the right team working on the right processes at the right time. Seastar will enable the U.S. to responsibly use the nation's immense shale resources and meet our chemicals and energy opportunities. Together, we will build the bridge to a renewable future.
Okay, well, good afternoon, everyone. It's a pleasure to be here with you. My presentation will be quite different from the ones that you've heard so far, and I guess the ones that you continue to hear today. We are about downstream operations. But one interesting aspect that I will not touch too much, at least during the talk, but maybe over the questions, is how we can combine upstream operations with downstream operations and with renewable energy. So this is, of course, many companies in the US are already doing that. It's a huge opportunity to move forward on the challenges that we have with energy. So the motto of our center is responsibly realizing the potential of shale gas. And our idea here is this is not the ultimate solution, as the video tried to convince you. It's a bridge fuel. So you've seen the video. And I guess the first point that I wanted to make to you, just to make sure that we are on the same page, is how much energy we use. And so I give you here the example of the United States. To your left, you see the sources of energy in the US, petroleum, natural gas, coal, renewable energy, and nuclear, which is used for electric power. So if you add all those, about 80% of this energy comes from fossil fuels. And the prosperity that we have, the world that we live today, it's all based on the fossil fuels. This has been, this infrastructure has been put in place for over 100 years, so it's very much in place. But the message here is the amount of this energy, right? So 80% of the energy, you could, what we have issues informing the public is that they say, okay, it's 80%, but just take it out and put the rest with renewables. Well, it's so much energy that we don't have, even the United States, so rich, We don't have the resources to be doing that, because you have not only to replace the source, but you'd have to have the distribution of this energy, and also the uses of that energy would have to be all different. So the cost for that is what makes it very difficult. So this graph also shows you where the energy is being used nowadays. So a lot of energy. So again, if you think about the magnitude of the use of energy, I told you on the video you saw, just for transportation fuels is 10 million barrels per day of oil. So the US uses about 19 million barrels per day of oil. So again, if you put this oil on barrels, and go across the United States, that would cover about 20,000 kilometers of barrels of oil. And it's every day, right? It's even, we can imagine how is it possible to move that much energy, right? So then just changing since 80% comes from the fossil fuels it's what the challenge is. So in terms of new technologies, of course, what is it that we need? We need technology that can generate vast amounts of energy. It needs to be cheap. It needs to be generate no CO2, no damage to the environment, and of course reliable, right? So, but because of the magnitude, we need the interim solution, and that's what we propose as a bridge fuel. And why shale? Because the ratio of hydrogen to carbon on a shale is almost 4:1. Right, so it's a fuel that, when used, will generate the least amount of CO2. It's also a fuel that's very clean. It's very low amounts of sulfur and nitrogen, until you can get into the renewable sources. So with that in mind, then the National Science Foundation in the United States, they have a program where they call engineering research centers. And if you have an idea that you believe is very important for the country and for the world, and that you need a team of experts, then they would like to fund such a center. One of the advantages, it runs for 10 years, so we can think about long-term type of research. Also, we have their partnership. They help us to reach to other agencies in the United States and around the world. So the idea is to form an innovation ecosystem of companies, government agencies, non-government agencies, the public, so that we think about how to address the many issues that we have. Of course, the center uses the objective is to develop new science and engineering that is geared into solving the issues at hand. That is done with the help of industry. So we have industrial partners that work with us. Currently 26 companies that they go across the value chain, the stakeholders in many different areas that help us to focus, make sure that we're doing the best possible engineering. We also have as a mission, and I'm glad to be here and see the students. We want to make sure that we have give the students the best possible education, because they are going to be the ones who, of course, are going to drive those ideas forward. And we do all that in an inclusive environment. So in our center, people of all kinds of faiths and ideas, they are welcome. We discuss ideas, and in fact, we need very different people with different backgrounds to be able to solve such a difficult problem. Now, in terms of the technical challenges, I thought that I wouldn't go much into details with you on that. What is the particular chemistry that we're looking at, except to tell you that the innovations that we are working on they are much more efficient than are currently available, and this is due to the type of hydrocarbons that are available on shale resources. And the U.S. has the equivalent of 100 years of energy, enough to power the country for 100 years. And as I'm going to show you, this is also around the world. We have that same energy. Of course, this generates jobs and the economy and what can be done. But the important part is to do all that responsibly. So here is a map showing the shale resources around the world. And I think that the two countries to look at is China and the United States. The first and second largest resources of shale, and also the first and second producer of CO2 in the world. So if there could be a transition from coal, especially in China, right? In China, as you may know, it's that fuel is very strategic for them, so they are not going to not use coal unless they have another fuel, and they have the largest reserves of shale in the world. So if they could learn how to use those resources, the amount of CO2 could possibly go down by a factor of 2 from the largest emitter of CO2. So this will be huge. And as I mentioned to you about bridge fuel, the plan here is to go from fossil fuels to non-fossil fuels. As I mentioned to you, because of the magnitude, we cannot immediately replace that with renewables. But over this transition, the challenge for us is do that in a way that generates the least amount of CO2. So, of course, how are we going to do all this? So here is an example of technologies. I'm old enough that when I was in the Silicon Valley and I saw the first cell phone, I was laughing at it. I said, well, this is never going to work. And for the reasons that you see on the bottom, I used to use those public phones that were everywhere. So it's much easier. Why this complicated thing is never going to work? But of course, you've seen what happened with that. So technology has the highest potential, is the greatest uncertainty. I'm not here to tell you what the future is going to be. Nobody knows. But what we have to do now, we know what to do with the technologies that we have. And that's what we are concentrating on to find out where to go. And we believe that the shale resources as a bridge fuel has the potential of getting us where we need to be out of fossil fuels, and on that journey generating the least amount of CO2. So that's the message I wanted to give to you, and especially for the students, we could have many things to discuss, and I hope you will be asking lots of questions. Thank you.
Thank you very much. Any questions? Yes.
Hi. Great talk. Thanks. I was just wondering, if you bring in all of this new infrastructure for shale gas, how do you guarantee that it's going to be just a bridge fuel and not used for that 100-year period?
Well, we cannot, right? And what we can do is offer an option, and then the public and the companies and the governments are the ones that will need to move forward. So we're not trying to we're trying to inform and give you the tools, and I think that the governments are going to be the ones that are going to make sure that this transition happens, right? That you need to have the government funding the new technologies in this area. What we know is that if we make this transition now, is the quickest way that we can get into getting the CO2 down, because if you as soon as you change an energy source, there are the costs of that transition. It's so expensive, and if you want, I can give you some numbers of how much it would cost to go from fossil fuels to electrical. If we could do it, then it's many times the U.S. GNP for a few years, right? So how are you going to do that? Well, it's going to take time. So let's do something in terms of making processes that are more efficient. So then, very fast way of decreasing CO2 and a better fuel, so it can go down. But you are correct, right? That we need to make sure that we have a better fuel now that's so much better, but let's not stop there. Let's continue, right?
Yes. How do you plan to manage the social acceptability of these?
Well, with help from people like you. So. Right. So it is a challenge, and I like to say that we're not trying to educate the public. We're trying to give them the facts so that they can say, here's the science, and here's how we move forward. But it is, we do quite a bit of work trying to tell people what this really is. Why is that we cannot just drop fossil fuels and all of us? It needs to be gradual. And if it needs to be gradual, there's this very painful mission for us. Unfortunately, I cannot offer, I wish I could offer, this is the final solution. We are not the final solution. We are the best solution on the way coming to a society maybe 30 years from now, if we're very lucky, maybe longer, that then we'll rearrange our society so we can really go completely into renewables.
Great. Andrea?
Yeah. Hi. I also have a question. So you say that shale gas produces less CO2 than other fossil fuels, natural gas, for instance, because of the ratio between hydrogen and carbon. Now, on an energy basis, how much less is this? So is it 50% less, 100% less? Or?
Yeah. That's a very good question, Andrea. Like I guess your group mentioned, life cycle analysis is very important on this, right? So, for example, if you're dealing with shale, right, you deal with natural gas, and you have to absolutely make sure on your life cycle analysis that when you're producing your shale, that natural gas is not escaping into the atmosphere, because then you gain in one place, you lose into the other. So it's a difficult question to answer. There are many pieces over there. So if you have just the fuel by itself, also depending on what kind of fuel you use, what your process is, also because we're going to be spending energy into making a fuel. So if you start with methane, it's the best possible fuel. We have the highest density of energy. That's what nature gives. I wish we could use that fuel directly, but unfortunately we can't use it directly. Whenever you transform natural gas into some other things, right, then you start degrading it. And then also you need to make sure that when you're producing it, you don't let it escape. Then you have to look into all those things very carefully, new technologies, new ways of looking into that. So to answer your question, for example, if you go coal, that would be easier to answer. If you go from coal to natural gas, you get about half of the CO2, right? So especially with our Chinese friends, they have to rely on coal. That's the energy that they have easily, right? So they are not going to dismiss that, right? Because in terms of their security, right, they have to be doing there. But like I said, if they could find a way of developing their shale resources, right, so then the amount of CO2 that they could they produce would go up by a half, and they are the largest emitter of CO2. That would be huge, right? If we could help them achieve that goal.
Okay, great. Can I invite the speakers of this session to join the panel? So we have a really amazing array of professionals today here that come from industry and academia, and also from very different countries where regulations differ significantly. So hopefully we can get some new answers here. So who has some questions for the panel?
I have a question for the geothermal energy system. So you're getting some fluids from granite in both situations. And I haven't heard you talking about the hydrogen that is potentially contained in these fluids. Is this something that's been measured, evaluated in terms of potential of carbon-free energy? So I'd like to have your opinion on that, or what you know about this.
Well, thank you for your question. Well, in our situation, we have a very low content of hydrocarbons. We have 0.5% methane in the brine, and but a major issue is carbon dioxide in the brine. We have roughly the same value of water, but carbon dioxide. If we depressurize the system, that's why the thermal water circuit has to be operated at least at a pressure of 21 bars, as the depressuring value of carbon dioxide is around 19.5 bars. So we keep the carbon dioxide in solution and return it back into the reservoir. So we are carbon dioxide free so far. No, as I mentioned, we just have a very small portion of methane in the brine, but no further hydrogens.
And for us, we don't know what's in the brine yet. We've got a little bit of work to do, and that would be something that's interesting from the production tests when we actually get a fluid sample.
Any more questions?
The question for Andrea, which I didn't have a chance to ask before. You show in your environmental analysis that you assess climate change. Could you tell us what are the proxies you're using to do this assessment?
What do you mean by proxies?
I mean, climate change is driven by, global warming potential or radiative forcing in the atmosphere. So it's kind of the physical aspects that leads to climate change and any temperature increase is fairly complex. Yeah. So what are the current physical processes that are included in the assessment?
Okay, so an easy answer is that so we use the models developed by the IPCC, the Intergovernmental Panel on Climate Change. So basically, I don't directly intervene in the model itself because, to be honest, they are much more expertise than me on that. I just apply their model to the model I calculate for the geothermal production. So basically, my job here is to construct this life cycle of the process and get all the data needed, and then apply the models, for instance, developed by the IPCC. I don't know whether I responded to your question.
Well, I mean, maybe you can clarify. You mentioned you're using the IPCC model. Yeah. What goes inside? What are the inputs to this model? Is that the gas emissions?
Okay, yeah, clearly. So basically, the IPCC model, you need to know the atmospheric emission of about 20, 30 greenhouse gases. So for instance, CO2, carbon dioxide, everybody knows that, but you also need to know, for instance, amount of methane emitted to air. For instance, methane is a greenhouse gas that is 25, 26 times more potent than CO2. Then you have other chlorofluorocarbons, which are 1,000 times more potent as greenhouse gases than CO2, and so forth. So basically, you need to know along throughout the life cycle of the process how much of each of these gases is emitted into air.
Okay, thank you.
I actually have a follow-up question that perhaps some of you can answer. So like in these models, for example, permeability enhancement, it's one of the factors that you said that increase the impact by 30%. But at the same time, when you enhance the permeability of your reservoir, then you give your reservoir longer time. And therefore, you're getting more energy out with the same initial investment.
Yeah.
So how can you compare the gains of enhancing a reservoir against the bad impacts, and perhaps you can clarify on what those are?
Okay. Okay. So basically, imagine you have a geothermal plant, okay? And the well and geothermal reservoir is so good that you don't need stimulation, okay? So and then compare this with another one where the geothermal reservoir is not that good, okay? If you're comparing these two, The first one, where you don't have to use any enhancement or stimulation techniques, of course performs better. That doesn't mean you don't have to apply or carry out any stimulation, but if you can prefer a higher quality, or if you can avoid to use this, or indeed if I can give you any recommendation on which one is better. So for instance, one of the outcome of my study is that from climate change impacts, so firstly the strategy should be you should apply a chemical stimulation because it has the lowest impact amongst all stimulation techniques. Then after that, the ranking would be hydraulic stimulation, and after that it would be a second leg production, a second leg in the production well. So I mean, they do increase the impact, but that's because of the conditions of the reservoir.
Okay, thank you. Jörg, do you have anything to add, perhaps, because
I think it's
you
a little
also
bit
have to
too
deal...
theoretical, as I don't think that you will find two different geothermal systems with the same conditions. Once doesn't need any stimulation, and the other one can only be developed by stimulation. And well, just having a look at United Downs in Cornwall, you have a tremendous high temperature of 195 degrees C. Probably you will need some stimulation to get your thermal water circuit running. Of course, you will have some carbon dioxide effects, but by the end, the energy output will be a lot higher than in comparison to, for example, to our geothermal brine system, which we are running with 165 degrees C. We will gain at least 2 megawatt electricity more just through this higher temperature, and this will compensate the higher carbon dioxide footprint.
I mean, I agree. I totally agree. What I'm saying is that if you don't need it, it's better. If you need it, you need it. But I agree.
Yes.
Okay, any more questions? Yeah.
Yes, I would like to discuss about the waste disposal, waste management. Is it an issue, challenges? Do you think you currently have solutions already available, or do you think we need more research on this research program on these topics? I would like to have your point of view.
Well, finally, within the last year, we developed a solution we can actually live within, but we are not finally happy. Therefore, we are actually involved in 3 R&D projects to develop further inhibitor solutions to prevent heavy metals from scaling, especially the ones like lead-210, which occurs this natural occurring radioactive problems. This works quite well so far, but we intend that we can achieve a further reduction of residues, and the final idea is to keep the scales in the system and to return them back into the reservoir.
Any more questions?
It's been interesting to me that the 2 power plants that we've had information about, potential ones, are both producing about 3 or 4 megawatts, which is not very much. In the UK, we have an offshore wind turbine demonstrator where each turbine is 8 megawatts. And we've recently opened a wind farm which produces 400 megawatts. How can the geothermal industry scale up, increase its capacity? Because in a way, each of your power plants is equivalent to 1 offshore wind turbine with the current technology.
Well, for the UK, our project is very much a pilot project. And originally, when they went out to do it, they were looking at doing a 10 megawatt power plant. This is very much pilot, and if it works, then yeah, there's scope to scale it up with similar structures and similar granites. But we have to make sure it works first. We have to get the technology right.
So to make it equivalent to, say, 1 medium-sized offshore wind farm, you need 40 installations of the sort that you have now. Would they all be drilled from the same place?
Well, I think our site has the potential to generate more than we will be for this. So say our site has a lot more potential when we start testing and things, and you can actually generate 5 megawatts. If you expanded the amount of wells that you drilled, then then you could upscale it more easily. But you're right, there would be a balancing act to see how many sites that we need to generate the same as a medium scale wind farm, and whether that would just be increasing the wells into the same structure, or doing doing more projects in different areas. We'd have to see how that fits in, but we've got to prove it works first.
Right, over there, do we have a question?
Thank you very much. Thank you for your presentations. So this question's first and foremost for Fabio, but I'd like to also ask the panels for your opinion on a similar question for before, but I would like an overview answer about shale gas actually being a fuel bridge, or if you think it might actually crowd out renewables, and whether using shale gas as a temporary option may take the resources that should be actually used for the renewable options.
Yeah, so that's one question that we get quite often. So the shale is not a replacement, it's a bridge fuel, right? So the message that we try to give is that you can let people just build more coal plants, and if you look how many new coal plants are being built per year, just in China, is on the hundreds, new ones. So because people need energy, and of course, I didn't talk about the population in many parts of the world that are going up, right? Where are they going to get all this energy? Well, it needs to be cheap, right? So then that's where they go, because there's an infrastructure for that. So I'm not saying that we should not invest money on other technologies. We do. So then the question here for us to decide, not for me, is what's the best way of getting from where we are right now, 80% fossil fuels, to completely renewables, emitting the least amount of CO2? So in my mind, or the predictions that we are doing, the best way would be to invest some on this very nice fuel. It's the best of fossil fuel we have, so that we can get into renewables the quickest way, emitting the least amount of CO2. The technologies are not very far away from what we have. It doesn't need something dramatic, but it's a question of improvements, right? Of being rational, and you say, okay, I know that I'm still emitting CO2, but I'm emitting much less. So then let's go for that, and then then as we get lower and lower, then we get rid of it. So maybe a good example, if you think about emissions on diesel, for example, right? 20 years ago, it was high, and now it's orders of magnitude lower, right? So what happens there is that people, they say, now give me less, and more strict emissions. There's a technology, and then new technologies are being developed, right? But they cannot just say, okay, no more diesel or gasoline engines, that's it, right? So you can't do that. So you have to go gradually, and that's the option that we are proposing. But you know, the question that you ask is, you need to invest money on and resources on new technologies. I mean, no question about it. It's not one or the other. You have to do the best option.
I have a very quick follow-up question on that. Do you think the policies are changing fast enough to allow to divide the budget of a country, or the money that is being invested in energy, into the right type of energy that we should invest in?
Well, this question is much higher than my level. I'm really low. I don't know. The government.
Well, may I give an answer? I think from the experience we've done or made in Germany, sometimes politics even decide too fast. If you look back to the Fukushima event a year ago, before the Fukushima catastrophe occurred, there was a public commitment with the nuclear power industry to enhance the runtime of the nuclear power plant for another 10 or 15 years. After Fukushima had occurred, half a year later, our Chancellor, Mrs. Merkel, then decided, just for political reasons, that we had to step out of nuclear power production. So I think this is not a reliable political discussion, especially from my personal point of view, need these technologies in combination with shale gas or with gas technologies to find a bridge, as we do not have the renewables available to compensate the missing fossil fuels at the moment.
Thank you. We have a question over here.
This one is following up, I guess, from the question 2 before now about the scale of the power plants. And the geothermal plants seem to be quite small scale, but site contingent and expensive to develop. And the other example was wind farms where they're really large. But this is, I guess, directed to Fabio. How important is that? You talked about sort of small scale processing and, I guess, mobility and be able to put the processing where the resources are. How important is that, and how important do you think the sort of I guess transferability or ability to put the same things in many different places in terms of developing a solution?
Yeah. So so this is a question about a distributed manufacturing, right? So right now on the chemical industry, if you're a chemical engineer, we are taught bigger is better and makes sense, as opposed to the economy of producing many of the same kind, right? So if you produce one-of-a-kind car, or you produce many of the same type, hundreds of thousands, right? The cost goes way down. So if the industry could be standardized, then the cost of manufacturing could go way down. Now, if you do a life cycle analysis, then so if you need to produce a chemical, instead of producing, for example, in the U.S., bringing the resources into one central facility, producing it and sending it back, right? Why don't you do it at the various places with units that are completely automated, much more efficient than where we are, so we save costs? Is a very different model than industry is used to. We think that there is a huge opportunity there, and if there is, then the chemical production, including of fuels, is going to change. And the answer for that is that it's going to be more efficient with the technologies we have currently, especially for shale that's so distributed in the United States, but also around the world. So that's then in terms of producing energy locally and chemicals and what people need, including talking about fertilizers and things that people need, plastics, and locally.
Thank you. We have a question over there.
Hello. Thank you for your presentations. I have a question for Fabio, I think. So obviously with shale gas, you're reducing the impacts, you're reducing the amount of CO2 compared to coal or oil. But as shale is not a completely new technology, but it's still being expanded on, is there not the worry that you might be creating issues in other areas? For example, like ground water leaching, water going into the ground, also all the space that it takes for a pad. Obviously you have multiple pads, you're going in multiple directions. It's going to take a lot of convincing people in the local area, and if you want to expand that to be the bridge fuel for such a large population in America, is that not something that you'd have trouble convincing them of, and all the other issues I mentioned as well?
Yeah. So to answer that question, you have to, if you're going to use shale or any resource or any mining operation, you have to do that responsibly. Otherwise, you can't do it. You cannot harm the environment. So, for example, in the case of shale, there are some deposits in the U.S. that are too close to the water tables. So those you don't touch. You just leave it there. The oil is there and so on, but you don't touch. There are some that are miles down, and there are some rocks and formations that are pretty impermeable. So you can go deep down and take the oil, and then when you're done, all the operations, they stay much below for example, water tables or harms that you can do to the environment. But the critical is to do that responsibly. So usually the very large companies, they have the technology, they understand it very well. Sometimes the smaller operators, and that could be a problem, right? Because they are so small, if they do something that's a disaster and they sue them, they say, well, sorry. Right? But a large company, they can't do that. So I mean, you mentioned well that this technology of hydraulic fracturing has been, the oil industry has been doing that, using that for 30, 40 years. I mean, it's not new technology. It's people put pieces of new technologies together that's called horizontal drilling and hydraulic fracturing, and they put it together. But it's not a technology that's very novel. It's just that the people put it together. But any mining operation, you just Google any, iron ore, and so if people don't do it right, it's a disaster, right? It's just. So people need to do that responsibly. So that's the answer.
And perhaps also in a more transparent way, like renewable energies are doing. Like to gain public acceptance, you have to be very transparent and show exactly what you're doing. Perhaps there is a lot of in this industry that we don't really know that's going on. So I think it's also important. We have another question here. Yes.
Thank you for your presentation. I want to ask the question about the shale gas. Firstly, in the U.S., the shale gas mining likely to cause risk of geological structure change. That's the first one. And the second one is, how is the market priced to ensure the profitability of energy plants? For a company, how to balance the technology and the costs? Thank you.
Yeah. So in terms of, I think your question of seismicity, right? It is an issue. So and in fact, if you know about the shale, the issue with shale is not the process of extracting the shale. Is after you do the extraction, you use a lot of water to break the rocks, and then when the oil and gas comes, there's a lot of water. Now that water now has a lot of salts dissolved and so on. You don't want that water. So then one way of disposing of that water is re-injecting, and that's what causes the seismicity and earthquakes and so on, is this re-injection of the water. So as I mentioned before, it needs to be done properly. So there are technologies, there are ways of doing that. So that to answer your question. So it's on the re-injection of water, and I'm not an expert on that, but it can be done properly. Now, your question about costs, I'm not sure if you understand. Is it the cost of extracting of the upstream of operations of shale?
Yes. How is the market price to ensure the profit of energy plants? How to balance the technology and the cost?
And the cost. Well, so at least in the U.S., all those operations are privately driven. So they will not. They need to be. They have a profit and they have a price, and they're doing their operation and looking into the costs, right? So, and then of course also that drives technology, right? So they're always improving and trying to do it much better to drive the costs down. But it is a major issue for them, because that's all in private hands. So profit is
right. But for example, for renewables like geothermal, is the government giving any kind of help, or like do you think the government should give some kind of help to renewables to mitigate this trade-off between like the technology that you need to use and the energy that you're getting?
It also always helps to have some sort of incentive for more development of renewables to happen. But to answer your question earlier, to go back to that, I understand there needs to be a bridge solution, but when you interweave politics with it, the issue is if that becomes more attractive to policymakers and also oil and gas firms, then the chance for renewables gets even further away, because investment might be further away if it's an easy option. So I guess it's a balancing act with that as well. The subsidies would help.
Yeah. Okay, well, thank you very much to all of you for your wonderful presentations and for giving us your opinion today. I think we can go for lunch now. Thank you.
Thank you.